Well, here's a daily quizkin. So give this a try, stop the video, try and solve for the answer, and I'll give you the answer in a minute. And then I'll also tell you where to go on the video to skip the solution if you got it right. Okay, let's write the equation for this reaction. First of all, aluminum is a metal. It's an element, and I'm just going to write Al. Iron 3 oxide, well, how would I write that? Iron is Fe3 plus in this case. Oxygen makes a 2 minus ion, so when I charge swap, I get Fe2O3. So aluminum is reacting with Fe2O3. And it's producing, there's my arrow, aluminum oxide. Well, aluminum is 3 plus, because it's column 3. Oxygen, of course, is 2 minus. We just saw that. And so Al2O3 is what we get when we charge swap. And iron, which is another element. It's not diatomic, so just Fe. And it turns out that to balance, all I need to do is put a 2 in front of the aluminum and a 2 in front of the iron. Okay, next question is, 41.5 grams of aluminum are available to react. What mass of aluminum oxide will be formed? Well, let's solve this. My balanced chemical equation I've reproduced up here, and here's the information that's given to me. I know that I have 41.5 grams of aluminum that are available to react, and I want to know how many grams of aluminum oxide will be formed from this. Well, the old saying says you can't cross the Grand Canyon without using the mole bridge, and so I'll have to convert this to moles before I can do any stoichiometry. So 41.5 grams of aluminum is my starting point. I've got to get that into moles, so I'll use molar mass, which for aluminum is 26.982 grams per mole. The grams will cancel out. Now I can do stoichiometry. I've got a mole ratio I can use to get rid of aluminum by putting moles of aluminum on the bottom, and I want moles of Al2O3 on the top because aluminum oxide has got to get in my answer. So the ratio is 1 aluminum oxide to 2 aluminums, and that comes right from the balanced chemical equation. Aluminum moles now cancel out, and I have moles of Al2O3. But that's not what I really want. I want grams, so I'll use molar mass of Al2O3 next, which is 101.781 grams per mole. Moles are now gone, and I have grams of Al2O3 in my answer, and that's just what I want. So now I just do some arithmetic. And the answer is 85.1 grams of Al2O3. When actual reactions take place, we have to deal with a few things that we haven't considered up until now. One is that you have one reactant, typically, unless things are really carefully planned out, you have one reactant that's going to get used up first. And when it's done, when it's used up, you can't produce any more product. And so it's called the limiting reactant because it limits how much product can be produced. Well, if one of them runs out first and the reaction stops and you still have some of the other stuff there, you have what are called excess reactants. Those remain after the reaction has ceased operating because you ran out of limiting reactant. How do you find out what the limiting reactant is? Well, let's use this example as a sort of a starting point. This gives us a balanced chemical equation. It gives us information about how much ammonia and how much oxygen are going to be reacted or mixed together. It won't all react. We want to know how much NO will be formed. Let's solve the problem. Okay, the balanced equation is written up here, and here's the information that we're given. We know we have 30.00 grams of ammonia, and we know we have 40.00 grams of oxygen available to react. Ultimately, we want to know how many grams of NO are produced, nitrogen monoxide. We don't really know that because if we start out assuming that we run out of ammonia, we'll get a different answer than if we start out assuming we run out of oxygen first. So let's figure this out. Here's what I do. I compare the two reactants to each other. So I just pick one of them as my starting point. It really doesn't matter which one. 30.00 grams of ammonia I'm going to pick. And from there, I do a stoichiometry calculation that tells me how many grams of oxygen will it take to use that up. And then I'll compare with how much I actually have and see if I have enough. First thing I have to do is convert to moles. Ammonia is 17.031 grams per mole. So with grams gone, I now have moles of ammonia. My ratio is 4 moles of ammonia for every 5 moles of oxygen, O2. So So now I've converted to moles of oxygen, but I want grams of oxygen. This isn't just ordinary oxygen. Keep in mind that this is O2, so I can't put 15.999 in there, which is what you get off the periodic table. This is actually 31.998 if you double it, grams per mole. With moles canceled, now grams is all I have to deal with, and I have grams of O2. I do the calculation, it shows me that 70.46 grams of oxygen are needed to use up all of this ammonia. Do I have that much? No, I don't. I only have 40 grams of oxygen. So since that's my limiting reactant, that has to be my starting point in determining how much NO will be produced. So that's my next step, another calculation. 40.00 grams of oxygen. We now know that oxygen's molar mass is 31.998 grams per mole. The mole ratio is 5 moles of oxygen for every 4 moles of NO that are produced. So now we're in moles of NO, and we want grams, so I use the molar mass of NO, which is 30.006 grams per mole. Answer is now going to be grams of NO, and numerically it's 30.01 grams of NO. When we do actual reactions, they don't always come out the way we'd expect. For various reasons, we might lose some product. There are several reasons for this. One is that you might have a product that's volatile, it evaporates real easily, and so it's really hard to catch it all. Another one could be there could be a secondary reaction where the reactant is reacting with one of the products to produce something else that's unexpected. Or maybe the two reactants can combine in two different ways, and so you end up getting other products than you were expecting. So actual yield and theoretical yield are not always the same. The actual yield is what you actually get. Sometimes this is called lab yield. And the theoretical yield, this is the calculated amount. This is like the maximum possible. So this is sometimes called the paper yield. How do we deal with this? Well, one of the tools that chemists use to keep track of this is something called percent yield. Percent yield just describes how far did the reaction actually go in producing the theoretical yield. Mathematically, here's what it looks like. Percent yield is the actual yield, the smaller number typically, which you usually get in the lab, divided by the theoretical yield, which is the maximum amount that you calculate. And then, of course, you multiply it by 100 to get a percent. Like in this reaction, you have ammonia being produced by the reaction between nitrogen and hydrogen. Balanced chemical equation is given here. You have 50 grams of each, nitrogen and hydrogen, and you get 56.7 grams of ammonia. The question is, what's the percent yield? Well, to get this, we have to find out what's the actual yield and then divide it by the theoretical yield. Well, the actual yield we already know, 56.7 grams. Let's calculate the theoretical yield. Here's our reaction. It's reproduced. We say that we're starting with 50.0 grams of nitrogen and 50.0 grams of hydrogen, and the actual yield that we get is we get 56.7 grams of ammonia. That's actual yield. We need to calculate theoretical now. Well, we have information about both reactants, so we have to figure out the limiting reactant before we can solve this problem. So I'll start out with 50.0 grams of nitrogen, and I'll determine how many grams of hydrogen does it take to use that up. Nitrogen is diatomic here, so I'll double the molar mass in the periodic table to get 28.014 grams per mole. Now I have moles of nitrogen. The mole ratio is every 1 mole of nitrogen consumes 3 moles of hydrogen. I've converted between species now, and I just have to convert hydrogen moles into hydrogen mass. Well, the grams per mole for hydrogen are 2.016 because, again, it's diatomic. So the grams of hydrogen needed will be 10.8 grams of hydrogen. If I look at what the problem tells me, I have 50 grams, so I have plenty of hydrogen. Hydrogen is not the problem here. I will run out of nitrogen first. That means nitrogen is the limiting reactant. So 50.0 grams of nitrogen being my starting point again, I now want to figure out what's my theoretical yield of ammonia. Well, 28.014 we calculated was the mass of a mole of nitrogen. Now the mole ratio is, again, 1 mole of nitrogen on the bottom, but now it's 2 moles of ammonia on the top. I've converted to moles of ammonia, but I need grams of ammonia, and ammonia has a molar mass of 17.031 grams per mole. When the moles drop out, I end up with my theoretical yield of grams of ammonia. The answer is 60.8 grams of ammonia. That's the theoretical yield. That's how much we should be able to get if everything went perfectly well. We didn't actually get that. We got 56.7 grams. So the percent yield that we're looking for here is going to be the actual yield of 56.7 grams divided by the theoretical yield of 60.8 grams, and then change to a percentage by multiplying by 100. This comes out to 93.3%. So that tells you that if you do this reaction again, you can expect to only get about 93.3% of what you could possibly get.